Okay, good morning. Today we'll wrap up chapter 6. We have two more circuits left, basically the two resonant circuits, and then I'll go over the basics of a Bode plot. Okay, so it shouldn't take long. All right, so let's go over to our notebook and okay, first up is the series resonant circuit. Now, resonance is a phenomenon that occurs in nature. We all have at some point come across examples of mechanical resonance. So here's an example of series of electrical resonance. And what happens here is we have two energy storage devices, R, L, and C. L and C. And the circuit is a RLC circuit. So if this circuit receives incoming signals with varying frequencies, it so happens that at one particular frequency signal, the impedance of a capacitor and the inductor are exactly equal in magnitude. Okay, remember, these are energy storage devices, so the energy transfer takes place over a finite period of time. And at one particular frequency, what happens with this energy transfer is that the impedance of the inductor and the impedance of the capacitor are exactly equal in magnitude, but they are opposite in phase. And so they cancel each other out. So if I was to find ZLC, meaning the total equivalent impedance of the capacitor and the inductor, it will turn out to be 0. And you could perform this math. It is simply the equations of ZL and ZC. You equate them to each other and set F equals F0, or basically the same value, right? 1 over 2 pi FC equals 2 pi FL. And if you add those two together with frequency F value the same, it would turn out to be equal to 0. Now, to be clear, the magnitudes are the same. So if you just add the magnitudes, it will be twice as much. But the phase or the phase angles are exactly opposite. So if I was to draw, let's say, the vector for the inductor impedance, ZL, it would be a vector with an angle. And then, because it has the same magnitude and length, but opposite in phase, it would come back to that original point. Meaning if you add those two together, that vector, that phasor would go to a certain place and then return back to that certain point. And this is ZC, the result being zero. Okay, the result being that it turns out to be 0. That is just a graphical representation. We can, of course, do it analytically by just adding up the equations also. The frequency at which this takes place is known as the resonant frequency F0. Okay, F0. And that is the resonant frequency. But the cumulative effect of the inductor impedance and the capacitor impedance reducing to 0 is that it behaves like a short circuit. So ZLC goes to 0 means inductor and capacitor in series are behaving like a short circuit. The energy flows out of the inductor and goes into the capacitor, and then flows out of the capacitor, goes into the inductor. So it keeps bouncing back and forth between the two. Okay, that's what's happening to the energy transfer. We are not looking at the energy transfer analysis, right? But that's what's happening physically. But the cumulative effect of both inductor and capacitor in series at that particular point in the frequency is that it equals to 0. So it behaves like a short circuit. If it behaves like a short circuit, then ZEQ, the total equivalent impedance of this RLC circuit, is simply the resistor R. Make sense? ZEQ would be R plus ZL plus ZC. But ZL plus ZC is equal to 0, goes to 0. So only thing left is R. And so ZEQ is equal to R, the total equivalent impedance, ZEQ. And because this is a series circuit, that ZEQ is also labeled as ZS. ZS. Okay. That's just the notation. Doesn't mean anything else beyond that. Okay, ZS. So does this make sense? Right? And because the impedance is at a minimum at this point, because for every other value of the frequency, it would be R plus ZL plus ZC. There would be some value of ZL and ZC. So the impedance would be much higher than R, obviously, because now you have extra components in there. And so the V out would be less at any other frequency. So at resonant frequency, V out goes to maximum. Okay, V out goes to maximum. It's purely resistive. The V out goes to maximum. For every other frequency, V out is much less than the maximum. Maximum, of course, would simply be V in, right? You're applying an input voltage. If you allow the input voltage to reach at the output, the maximum value of the output would be equal to V in. So V out to V in. If you take those values and you plot it versus the frequency input, you would obtain a chart that looks like this, where the maximum is right here. And that max occurs at a frequency of F0. Okay, F0, right there. And that's the max. And because this is showing the normalized value of the transfer function, maximum value of that resistor voltage, V out, would be equal to Vs, the input voltage, right? So if the ratio transfer function, maximum would be 1. For all other frequencies higher than or lower than F0, the value of VR would be less than V in. And so it'd be less than 1. And the result of plotting these values as a function of the frequency gives us a characteristic of a band pass filter. So this works like a band pass filter. Does that make sense? Right? Now, ideal filters, of course, have a sharp cutoff. So an ideal bandpass filter would simply be like a rectangle which has a pass band in the middle, and everything else would be blocked, right? Everything else outside of the pass band is blocked. That would be an ideal characteristic, just a straight up band of frequencies with a sharp cutoff. Now, real life, of course, does not work that way. So it'll have a gentle slope on both sides. So the demarcation line between pass and block is again described in terms of the power. The point at which the power drops or goes above 50% is the point between the pass band and the block band. And because this is a band pass, meaning there's a band of frequencies, there are 2 cutoff frequencies, but the principle remains the same. You find the value where the power drops to 50% of the input power. Everything else above is is passed, everything else outside is cut off or blocked. Okay, and so 0.5 times P in, or a value of P out 0.5 times P in, translates to 70% of the voltage. Voltage is P is V square over R, right? So the voltage is square root of the power. So it translates to 70%, or 0.707 of V in. That intersects this curve in two places. So you get two cutoff frequencies. You have two cutoff frequencies. Everything else outside of those frequencies is considered to be blocked, even though we still receive some level of that voltage or power, right? Even though we are receiving a certain percentage of that input, we still consider that to be as blocked. Okay. All right, 10-second pause. Let me know if you have any questions. Q, I will explain in just a minute. Yeah. So I said that this happens only at one single particular frequency, right? So we take the impedance of the inductor and equate it with the impedance of the capacitor. So ZL equals ZC. ZL is J 2 pi FL, or J omega L. ZC is 1 over J 2 pi FC. You bring the J's on one side, everything else on one side of the equation, and you take F on the other side of the equation. You set the frequencies for both together, and you obtain an expression in terms of the components. So the resonant frequency F0 is described by the value of the capacitor and the inductor as 1 over 2 pi root of LC. We can also describe it in terms of omega. So omega 0 is simply 1 over root of LC. Omega is 2 pi F. You take 2 pi on the other side, you get 1 over root of LC. Yes. Yes, for a series resonant circuit, yes. Even for a parallel resonant circuit, it's the same. I could barely see you raise your hand. Everything's a blur. Can't read anything on the screen without my glasses. All right, so what was I saying? Yeah, resonant frequency F0 is given by 1 over 2 pi root of LC. It's a constant for that circuit, right? Because the value of that component is not going to change. Q describes the quality of this series resonant circuit to function as a filter. So Q is the quality that describes the functioning of the circuit. In terms of the components, you can describe it in terms of L and R, or R and C. Okay. L and R and R and C. The subscript S is just for series. So you have QS, you have FL, you have FH, but the S here just stands for the series circuit. When we get to parallel circuit, you will see QP, and QP is simply the reciprocals of these equations. And hence QP and QS are just reciprocals of each other. Okay, again, you do not have to memorize these equations. Okay, you can have them on your equation sheet for your homework assignments for the quiz. In terms of the bandwidth and the resonant frequency, if we want a circuit to work as a band pass filter, we want it to only pass a certain band of frequencies, right? We do not want a wide band. We always want a narrow band of frequencies. So in terms of the frequencies, we can describe the quality as the ratio of the resonant frequency to the bandwidth. The bandwidth is simply the distance or the difference of the two cutoff frequencies. Okay, it's how wide the band is. So B describes the bandwidth of the filter. It's the distance or the difference between the two frequencies. And then QS is the ratio of the resonant frequency to the bandwidth. Obviously, the wider the band, right? The wider the band, the higher the value of B, the lower the quality of the filter. You want the band to be as narrow as possible. Okay, you want the band to be as narrow as possible. And if the band is, yes, bandwidth is in hertz. If the band, if the characteristic and the bandwidth are very narrow, meaning they are very close together, we get a very symmetrical shape. We get a very symmetrical shape of the characteristic, right? And if it's very symmetrical, then we can say that the resonant frequency is about halfway between the two cutoff frequencies. Okay, so the higher the quality of the filter, meaning the narrower the bandwidth, the higher the quality. If QS is at least, I don't know, 5 to 10 times, if F0 is at least 5 to 10 times the bandwidth, meaning the value of Q is at least above 5, then we can state that the resonant frequency is about halfway between the two cutoff frequencies. And so the graph is, symmetrical. And then the FL and FH can simply be described in terms of the bandwidth and the resonant frequency, right? FH is about halfway ahead of F0 and FL is halfway below F0, right? Spaced equally apart. But in order for that to happen, the quality has to be high, at least 5 or larger. Okay, let's take a 10-second pause. Let me know if you have any questions. Any questions at all? Then it would not be, yeah. Let's see what happened here. That's weird. Okay. All right. So another way to look at the circuit is think of it in terms of the first order filters that we studied. Okay. This filter has two energy storage elements. Hence, it is a second order filter. It's a second order circuit. It's a second order filter. Okay. The previous ones that we looked at are RC and RL, one energy storage element, one differential equation, hence a first order circuit, hence a first order filter. So here, if you notice, it's a series connection of R, L, and C, series connection. And we take the output across the resistor. Output is taken across the resistor. Let's say the inductor was not present in the circuit, right? So I can draw the circuit like this. If you remember from last class, I drew a similar circuit for the RL and RC. Our output is being taken across the resistor. What if inductor was no longer present in the circuit? What kind of circuit would we have? It would be RC, and because the output is across the resistor, what kind of filter? No. There's only two options. It's fine. It takes a while. So we have a high pass filter if the inductor was no longer present. And the inductor RL filter is exactly the opposite. So if capacitor was not present in the circuit and it was just the inductor, what kind of filter would we have? Would we have a low pass filter, right? Output's being taken across both of those. So do you all see where I'm going with this? You have both a high pass and a low pass filter in the same circuit, and you bring both of them together, you get a band pass filter. So the characteristic of a high pass would look like this. This is a high pass filter, right? This is pass. This is all blocked, right? All frequencies higher than the cutoff frequencies are allowed to pass through. Then you attach it to a low pass filter. So this is the low pass filter. The low pass filters allows all of these frequencies to pass through, but it blocks all of these. And you brought both of them together, you now obtained a band pass filter. Okay, you have two cutoff frequencies. Depending on the values of the components, you would have the positioning of the two frequencies, and you got a band pass filter. Obviously, the closer these cutoff frequencies are, the narrower your band. What happens if they cross over? So you have FL and FH, but if you cross them over, what do you get? Nothing. Absolutely correct. In the middle of the band, you would not get anything. So if they cross over, you would get something like this, which is a band reject or a band stop filter. Yes. That will be the next point, and I will ask you that question. But does that make sense, right? You have two filters, you bring them together, you have a band pass filter. If you cross over the cutoff frequencies, you get a band stop or a band reject filter. Okay. But now we talked about, as I said, I talked about how, yes. Yes. Yeah. This will be a narrow band of frequencies that will be blocked. Yeah, absolutely. So certain use case for that kind of filter would be like a notch filter, 60 hertz line filter. So your power outlets are 60 hertz frequency. So if they interfere with your circuit, then you can install a line filter that will block out that 60 hertz signal. So it would not interfere with our circuit. That would be kind of like where you want to reject a narrow band of frequencies, but you want everything else to come into your circuit. Okay. So in this exact same RLC circuit, what happens if you take the output across the capacitor? It's a low pass filter. Across the inductor, high pass. And this is, going back to the beginning of chapter 6, a high quality crossover network, where a speaker can take an incoming cable and split it into 3 different outputs. It goes into 3 different speakers. And that's why I said a high quality speaker would have a high quality crossover network, should have high quality, huge inductors, capacitors, and resistors. Cheaper ones would simply be built out of capacitors. Okay. It would be a series RLC circuit, and it would do a very good job of filtering out. This would be the mids. This would be the bass, and this would be the treble frequency. So the same circuit, you can have 3 different filters depending on where you take the output. Okay. All right. So that's enough about the series resonant. So let's go. Excuse me, sorry. So the parallel resonant circuit works exactly the same manner. You have an inductor and a capacitor, both energy storage devices connected in the same circuit, but this time they're connected in parallel. The energy is still flowing in and out of the same two components. But this time, if I wish to find ZLC, it would be the reciprocal of the sum of the reciprocals. Okay, 1 over ZL, 1 over ZC. Okay, so this would give me which would be ZL plus ZC, meaning I'm dividing by 0, and so the effect of the capacitor and the inductor impedances would be that would tend towards infinity. So the parallel combination of the capacitor and inductor is effectively behaving like an open circuit. The exact same thing occurs at one single particular frequency, which is F0, the resonant frequency. The impedance of the capacitor and the impedance of the inductor are exactly equal in magnitude, but they're opposite in phase. But because they are connected in parallel, the total effect, the cumulative effect of both at the same time is that of an open circuit. Okay, the energy is just bouncing back and forth between the two. And they are not considered as part of the circuit, right? If it's an open circuit, nothing is going down there. All of the current coming from the source goes to the resistor. The effect is exactly the same as that of the series circuit. ZEQ in this case would be R plus infinity. So you would say it's R. Everything goes down the resistor. And V out is again at maximum for the resonant frequency. So when we plot this, we obtain a very similar plot. This circuit also works as a band pass filter. Band pass filter. Now, there are differences, of course, it's not the exact same graph. A parallel resonant circuit has a much wider characteristic. So the bandwidth is much wider than a series resonant circuit. And if you did the experiment in the lab in EE251, you would have noticed that when you plotted your data points, the parallel resonant circuit was a little bit wider. Okay. The equations remain the same. F0 is still 1 over 2 pi root of LC. QP, the quality of the circuit, is the reciprocal of QS. So in terms of the components, it is simply the reciprocal of QS. In terms of the resonant frequency and bandwidth, it is still exactly the same. QP is F0 over B. F0 over B. Everything else is still the same. It's no difference, no change. All right, 10-second pause. Let me know if you have any questions.
Professor.
Yes.
For lab, we had the parallel circuit with the 10K and the 50K.
Yes.
10K was in series where, let's say, like that white node is at the top, and the 50K,
Yes.
the 50K was where that R is. So that means the resistance that you use to calculate your frequency, your half frequencies would be them added together in series?
In parallel.
In parallel, okay.
In parallel, because the source would be shorted out, and so use them as in parallel.
Okay, okay,
Yep.
Thank you.
All right, any other questions about the resonant circuits? Well, then that's it for the filter circuits for chapter 6, right? There was a homework. The first homework was, of course, already done. The second homework was due tonight. I moved it or extended it to Saturday. So chapter 6, if you don't remember, again, has 3 homework assignments. First one is already done. The second one was due tonight, and the third one is due Sunday night. I extended the second one to Saturday night from Friday, just because it has a few more questions. But the questions in both homework assignments are, many of them are just short answer questions to reinforce the concepts. So they're, conceptual questions. There are some problems in there, and the problems are very similar to the ones that are solved in class. Okay, so you should not run into any issues. But if you do, please do not hesitate to reach out to me. I'll be available all weekend long via email as well as Zoom. So I'll be available today, tomorrow, and Sunday. And then again, quiz on chapter 6 on Monday. Okay, so if you have any concerns, just reach out to me. All right.
It's just on the filters.
Just on the filters. And as stated, chapter 6 will not be assessed on the final exam. It is already there on the final exam page. So go through it. I might just have one big problem spanning 120 points over 6 pages. I don't know. I haven't decided yet. Anyway, one last topic, and that is of Bode plots. Okay, Bode plots is named after H.W. Bode, who did a lot of research in this. It was a way to actually plot the frequency response of especially filters. Okay, frequency response of circuits, but especially filters. So in the olden days, before we had computers to do our automatic calculations, we'd have to plot everything manually, right? And so Bode plots were used then. They're still used today to perform quick analysis and write our plots. So what it is the plot of the magnitude of the transfer function as a versus the frequency. Okay, so we plot the magnitude of the transfer function h of f on the y-axis, and it's plotted as a function of the frequency, meaning frequency is on the x-axis. So the problem obviously is that the range of frequencies is very high. It's very large, right? Just the human audio range, human hearing range goes from tens of hertz all the way to thousands of hertz, 20 hertz to 20 kilohertz. So it's a very large frequency range. And then when you try to plot the magnitudes of the transfer function, again, there would be very small values to very large values. So there was a problem trying to actually actually plot all of these on the same chart. And so H.W. Bode was one attempt to actually, try to come up with a plot that would efficiently describe these large variations. So we are able to plot very small magnitudes to very large magnitudes all in the same plot versus the frequency range of very large to very small. Okay, so first we'll look at the x-axis, then we look at the y-axis. On the x-axis, we are plotting the frequencies. What we do is we plot it on the log scale. Okay, we plot it on the log scale. So you need to know what a decade is. A decade of frequencies is described as the log of the ratio of any two frequencies. If you take any two frequencies, F1 and F2, you take the ratio of the frequencies and you take the log of these frequencies to the base 10, that would give you the number of decades between those two frequencies. As an example, 10 and 100 has a ratio of 10. So log of 10 is 1, right? Log of 10 to the base 10 is 1, so you get 1 decade. If you take the ratio of 10 to 1000, it is 100. Log of 100 is 2. And right away, you can see how using the log scale, we have compressed a linear 10 to 1000 hertz into a small space, right? Into a small space. Octaves, we are not studying anything to do with octaves, but I just thought since we're talking about decades, I'll talk about octaves also. It's simply this, it's the same thing, except the base of the log is now 2, not 10. Octaves are generally used when we talk about like, singers, human singers, they say you can sing in like 7 octaves or 8 octaves. It's basically the ratio of 2 frequencies. You take the log of those frequencies to the base 2. Okay. All right. How many of you have used this kind of chart before? As an engineer, you may have come across this, you may have used it. If not, at some point you will. Okay. The graphs and charts that we use normally for everyday, everyday presentations, they are usually in the linear scale. Linear scale we add, right? 1 plus 2 plus 3 plus 4 and so on and so forth. So it's linear. If you wanted to plot thousands of frequencies on one chart, we need like a paper that's like a mile long. So instead of that, we use the log scale where each division is a multiplier, not a adder. We are not adding, we are multiplying. The log scale, and as the name describes, the log, is actually a division that is spaced apart in terms of the log of that division. So going from log 1 to log 2, oh, by the way, there is no 0 on a log scale, right? If you think about it. So log 2, starting from division 1, gives you a space of about 0.3. The value of log 2 is 0.3. So it's spaced about 30% of the way from 1 to the end. Log 3, of course, is 0.4. So from start at division number 1 to division number 3 is log of 3, and so on and so forth. So the log scale on a log chart actually describes the physical distance between each division. Okay, between each division. And so you would go from 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it goes to 10, 20, 30, 40, 50, 60. So it's a multiplier effect. And what that does is allows us to plot a wide range of frequencies compressed down to a very small chart. Okay. So the x-axis is on the log scale. If both axes are on the log scale, you would say it's a log graph or a log chart. If, as shown in this figure, one axis is on the log scale and the other one is on the linear scale, we get what is known as the linear log or the semi-log chart or a semi-log graph. Okay. X-axis is on the log scale, y-axis is linear, which is a semi-log chart. And at some point in your engineering careers, you would use this chart in your own fields. Okay. So as an example, this multiplier, let's start it at 10 raised to 1. So the next division would be 10 raised to 2, 10 raised to 3, 10 raised to 4, 10 raised to 5, and 10 raised to 6. And because it's a multiplier, every division has 9. Every big division has 9 small divisions. So this would be 1 into 10 raised to 1. So it gives me 10 hertz. The second division is not 11. It's 2 times 10 raised to 1. So it's 20. So 20 hertz, 30 hertz, 40, 50, 60, 70, 80, 90. And then the multiplier changes. So we get 100. So right there, I plotted 90 values in a very small space. Right? 90 values in a very small space. Then this becomes 10 raised to 3, 10 raised to 4, 10 raised to 5, all the way to 1 megahertz. I could go from 10 hertz to 1 million hertz, all in one small chart. If I was to plot this on a linear scale, I would need something like 10 miles long, perhaps. Just a guess. But at least a few miles long. Make sense? So you took a million data points, now all compressed onto one chart. Then on the y-axis, we do the exact same thing. And for that, audio engineers came up with a new value known as the bell. This was kind of invented around the time when engineers were trying to describe the loss in power, in transmitted power over telephone lines. So they came up with a new unit to describe it, which is basically just the ratio of the two powers. And it was named after Alexander Graham Bell. Absolutely. One bell is described as a log of the ratio of the two powers, P2 to P1, whether it's being transmitted or received, right? Doesn't matter. But they were trying to describe, again, a very large quantity and a very small quantity. To describe it efficiently and in numbers which made sense, they decided to take the ratio and the log of that ratio to the base 10. So it came about that one bell is the ratio, is the log of the ratio of two powers, log to the base 10 of P2 or P1. Then they decided they came across another problem, so they needed smaller divisions for each bell. And so they divided it into 10 further parts. Everyone remember the unit prefix table from from day 1, 9 weeks ago? Deci, centi, milli. Milli is 1,000. 1,000 part. Centi is 100 part. And deci is 1/10. So one bell became 10 decibels. Or it's more commonly known now as dB. So 1 dB is 10 times log of the ratio of the two powers, P2 or P1. And more commonly now is pronounced as decibel. Okay, not bell, just pronounced as bull. So 1 decibel is 10 times log of P2 over P1, short form dB. 3 dB level, a 3 dB level is the minimum that a human hearing can discern. So it's the minimum level where a human hearer or the average human can discern a difference in the audio level. Okay. But in terms of the power, it is actually a doubling of the power. Meaning if you have a 50-watt system, 50 watts being supplied to a speaker, in order to change the volume by enough so that we can appreciate a difference or we can detect a difference, you would need to double the power from 50 to 100 watts. It's the ratio of powers. So for a value of P2 that is twice as much as P1, the difference in decibels is only 3. High-end audio receivers do not have linear numbers. If you look at high-end audio systems, on the front panel, when you change the volume, it would not go from like 0, 1, 2, 3, 4. It would actually go in dBs, in decibels. Yes.
So P1 and P2 have powers.
Yes. So this, again, this began when telephone engineers were trying to quantify the power that was lost during transmission. So you would send a signal at one end and try to receive it at the other end. You would lose power, and they were trying to quantify the loss in power. Because again, remember, telephone landlines would run for miles, right? Very long distances. And so they needed a way to quantify that loss in power. That's where it comes from. But as it pertains to filters, we plot the transfer function, magnitude of the transfer function versus the frequency. Transfer function is the ratio of voltages, not power. So we wish to plot the transfer function h of f. H of f is V out to V in, the magnitude of V out to V in, right? So we would translate dB for volts or for voltages. since power P is V square or R, when you take the square on the other side and multiplies by 2, and you get this equation. Decibel for voltage for volts is 20 times log of V2 to V1. So when we describe transfer functions in decibel, the equation is 20 times log to the base 10 of the magnitude of HF. Again, HF is the ratio of the output voltage to input voltage. So if you wish to compress and describe H of F in terms of decibel values, then it's 20 times log of HF. And now we have taken our y-axis values and using the unit decibels, compressed it down to a very small range. Make sense? We took our frequency on the x-axis and you plotted it on a log scale, so we compressed it. So we compress it after we plot it. We do not compress the values. But the y-axis, we actually compress it by taking the log and then plotting those log values on a linear scale. So even though the chart says linear scale, the values are already compressed. Hence, we do not use a log scale, we simply use a linear scale. And so a very large range of values can be plotted on the x-axis, and a very large range of values can be plotted on the y-axis. Make sense? And thus, we obtain what is known as Bode plots. Bode plots are straight line approximations of certain areas of the frequency response. So whether it is a low pass filter or a high pass filter, we can use Bode plots to describe those. Each of these has a slope, and the slope always has a value of 20 dB per decade. If it's a low pass filter, after the cutoff frequency, it starts to lose voltages, right? It starts to lose the power, excuse me. And the slope of that has a value of 20 decibels for every decade change in frequency, meaning as you go along on the x-axis, the slope starts losing value at 20 decibels for every decade. It's the exact opposite when it's a high pass filter. The slope is still 20 dB per decade. Yes.
So it's above this negative, the out the front.
Yes. Yeah. Yep. And this value, 20 dB per decade, is true for all first order filters. Okay. All first order filters. For a second order filter, the slope will be 40 dB per decade of frequencies. For a third order filter, it would be 60, fourth order filter, 80, so on and so forth. So it means the higher the order of the filter, the sharper and steeper the slope of that transfer function. Remember, I mentioned this on the first day of, the first day of chapter 6. You have nth order filters where EE students study filters by a separate course by themselves. So the higher the order of the filters, the sharper, the steeper the slope of those filters. And so in terms of the dB ratio, it goes 20, 40, 60, 80, so on and so forth. Okay. All right. That is the end of chapter 6. Any questions? Questions at all? Yes.
So can you explain why that's not? It's like that.
Why does it look like that? Like, so this is for a low pass filter, which a low pass filter would be like this. And a high pass filter would, of course, be like this. Right? So that's what it is. But it doesn't matter what kind of filter it is, it will have a slope. And the slope will always have be approximated in a Bode plot with a value of 20 dB per decade. That slope will always have a value of 20 decibels per decade.
So you're approximating with that straight line.
Yes. We're approximating with that straight line. Yep. All right. I mean, filter design is very complex. There are engineers who spend their entire careers just doing that. So there are lots and lots and lots of considerations. Yeah. And I'm still around. I mean, while I pack up, if students have any questions, I'm happy to answer those.